Well, you might recognize this big blue Miller welder from many of my previous videos where I've needed a good strong AC current source to test the ampacity of wires or trip circuit breakers or whatever. Well, the neat thing about a vintage welder like this is there are no modern electronics in it at all. In fact, to generate the somewhat crude constant current that's needed for a welder, they use nothing but a giant transformer. But that transformer is not quite the same as a typical power transformer. It actually has a leaky magnetic circuit that allows one to shunt some of the magnetic field in the core between the primary and the secondary. So we're going to take a look and see what's inside a welder like this one and figure out how it works. Now, this thing is too heavy to lift onto the workbench and open up, so I'm going to use its smaller cousin over here. This is a 120 volt 20 amp welder. It's actually a welder that I bought when I was a teenager, probably for about $100 or so, and I learned to weld with it even though its output current of 100 amps is so limiting that you can't really weld anything of any thickness, but it did work. The interesting thing for me was, well, it's the first time I ever saw a funny plug like this, a 20 amp plug where one of the blades is 90 degrees to the other. And what came with it was a receptacle, just like this one, with instructions that what you should do is replace the receptacle wherever you wanted to use the welder with the 20 amp one, and presumably something like swap the fuse to a 20 amp fuse and you'll be fine. Well, that certainly shows you how standards and electrical advice have changed over the decades. You sure wouldn't suggest anything like that today. The good news is I didn't burn down a house or anything like that, but I did learn how to weld. So what we'll do is put this welder on the workbench, take the cover off, and see what's inside. And that's what's inside the welder. If we look at the transformer, here's the primary attached to AC, and over here is the secondary with these somewhat thicker, but not as thick as I would have expected, wires. And you can see there's a big giant core, an E-type core, sort of shaped like an E from one side. And this is the magic mechanism that allows us to adjust the amount of current we want for our specific welding job. And it does that by raising and lowering this mechanism through the center of the core. And what is that mechanism? Well, if we get up close, what you can see here is there's a piece of steel embedded behind this brown material, whatever it might be. And as we lower this, that piece of steel produces a magnetic path between this part of the core and the center of the core. So instead of the magnetic flux having to flow completely around the core like that, now some of the flux can flow through this shunt, this magnetic shunt, and completely bypass the secondary. So how does that limit the current? Well, to understand that, we need to understand a bit about how a power transformer works. I did a nice video on it, and if you want the details, you can look at that. But very briefly, in a regular power transformer, what happens is we have a primary attached to the AC power, and the voltage applied starts a current flowing in the primary. That current creates a magnetic flux through the core, and that flux increases until it induces a voltage in that primary that is almost equal to the incoming AC voltage. And when that happens, well, you limit the amount of current going into the primary to that amount. That's the magnetization current. That's how an inductor works. And all that really means is we get a certain current keeping a certain flux flowing in the core. Now, we go over to our secondary, normally if we attached a load here, we get some current flowing in the secondary, and it turns out that current creates a magnetic field that opposes the magnetic field in the core. And by opposing the magnetic field, well, the flux is now less. With less flux in the primary, the voltage across the primary is not high enough to oppose the incoming AC. So we get more current going through the primary to increase the magnetic field, to bring the flux back up to a value to essentially make the voltage across the primary equal to the incoming AC voltage. And it turns out that additional current that's flowing in the primary corresponds exactly to the additional current that's being drawn from the secondary. So that's how a normal transformer works. Well, that's all good and well. What happens in a normal transformer if we short the secondary, as we might do when we're striking an arc in a welding operation? Well, with that secondary shorted, what it means is there can be no flux flowing through this part of the core. And that's because there is no voltage across this coil. And the condition for that is no flux. In a normal transformer without a shunt, well, that means there's no flux in the primary, which means the primary tries and draws more and more current to produce a flux, enough to produce a voltage equal to the incoming AC. Well, what essentially happens is it starts drawing so much current that things start melting and all sorts of interesting sparks start flying, which is generally not desirable. Well, we don't want that to happen. The nice thing is with our shunt in here, what that means is instead of this thing producing zero magnetic flux through the entire core, yes, it produces zero magnetic flux through this part of the core, but the nice thing for the primary is, with this shunt over here, well, there's a certain amount of flux that still can get around. And it's certainly less than it was before we shorted that, but what essentially happens is when we short that, we get still a significant flux flowing here, even though there's no flux here. We need more flux here to make the voltage in the primary equal to the incoming AC voltage. Well, that's simple. The current in the primary is increased until the amount of flux through this magnetic circuit, through the shunt, is enough to create a voltage in the primary equal to the AC voltage. And so maybe 2 or 3 or more times the normal current through the magnetic core now flows, and it's still limited to whatever the specs are for these windings, and everything is fine. So essentially, we still have transformer action when we're not shorting the secondary, and that's essentially an output voltage determined by the turns ratio in the transformer. And when we short the secondary, we now essentially remove this part of the magnetic circuit entirely. However, by shorting it, we do have a large current flowing here to keep this flux through this portion to zero, and that produces our maximum current point. Normally, when we're drawing power, where you need a voltage and a current, as opposed to zero voltage in a short or full voltage and no current, you have something in between. So you get a nice voltage current curve that goes from a maximum voltage to a maximum current. And we should look at that in a schematic diagram. So how can we represent a welding transformer? Well, this is the standard model of any transformer. We have an inductor and a resistor. We'll call this R1 and X1. And R1 represents the resistance of the primary coil. And we'll set up another resistor here, R2, representing the resistance of the secondary coil. And there'll be a corresponding inductor. We'll call it X2. And we'll also put in an inductor to represent the magnetizing current and a corresponding resistance, which we'll call Rm. And that is almost our model of a transformer, with one more thing to add, and that is what we'll actually do here is put in an absolutely perfect ideal transformer like that, with the appropriate number of turns on each side. And that's the generalized model of a transformer, but it turns out that for what we're doing, well, there's only one thing that's really of interest. Okay, two, one of which is, of course, the primary and secondary turns. In other words, how much the voltage is reduced. But the other thing that is the dominating element are these two inductances. And so we can make our model look something like this. Again, the ideal transformer over here with not a bit of loss. And now we'll put in our combined coil. We'll call it X12. And that is the model of the welding transformer. And, well, how do we use it? Well, the first thing is really what's of interest is how much is the voltage being reduced across the ideal transformer, and how big is this inductor? Well, it turns out that it's fairly easy to find out. And, well, over here is V in. We generally know what that is. And the output here, we'll call it Vs for the secondary voltage. Well, that is the same as what we would measure across here in an open circuit condition. So we'll call this VOC, and so we can say Vs equals VOC for open circuit. In other words, to find out what this voltage is, all we do is we put a voltmeter across here and measure the voltage, and we're done. That'll give us the secondary voltage right there. Now, what is this inductor? Well, what would happen if we were to, in fact, attach some wires here and short it? So we got a short circuit current called ISC. Well, how could we use ISC? Well, quite simply, using Ohm's law, X12, the reactance, equals VOC over ISC. So that's indeed what we should compute for our welder. We'll do it for the Miller welder, and we'll compute this both for the shunt setting at 225 amps and at 50 amps and see how this inductance changes. Oh, and one more thing. What we'll do is when we're driving the big Miller welder, we'll only drive it with 120 volts because, well, in the end, this inductance doesn't actually change depending on the input voltage. So by driving it at 120 volts, well, the currents over here will be at much more manageable levels. Okay, so to do our open circuit and short circuit tests, well, I have the welder set up, the good old Miller welder. We'll use that one. And I have it hooked through this adapter plug to 120 volts because, well, it really doesn't matter in terms of inductances what the applied voltage is, and that'll keep currents to a manageable limit. And I don't have a 240 volt outlet in the workshop. So the first thing we're going to do is use a voltmeter to get the open circuit voltage. And I should point out I have it on the high current setting and at somewhere around 225 amps on the shunt dial. And we have the trusty old voltmeter here, and I'm just going to lay this probe there. Hopefully that'll get it good enough. And I'm going to switch it on. And what do we get? We get about 31 volts. So a relatively low voltage, and that's exactly what we would expect. Now that we've done that, what we're going to do is get the short circuit current. So I'm going to take the trusty ammeter Tesmen donated and just put it around the wire, and we'll take our return current thing and connect it. So we've got a short here. I'm going to move this over because I don't want to melt the current. I don't want to melt the insulation on my welder cable. And, well, we'll turn on the welder and see what we get. We get about 139.5 amps. Now, what we'll do is we will test that with the current setting dialed all the way down and see what we get with that. So as we're dialing this down, we're pushing the shunt more and more between the primary and secondary. So more and more flux will be shunted. This is getting harder to turn. Probably hasn't been dialed this far down in a long time, maybe in 50 years. I'm going to set it to 50 amps. There we go. So once again, we'll look at the ammeter. 23.8 amps. Makes sense, we're at half the normal input voltage. And now we'll go back to voltage measuring mode. So there the two probes are connected. And once again, we'll turn it on. And look here. What do we get? 29.3.4 type voltage. So you can see there's not a huge change in voltage between the low and high current settings, but there's a significant change in current. So for the 225 amp setting on our adjustable magnetic shunt, well, what did we get? We got a VOC equals 31 volts. So that's with 120 volts in, so we would expect double or 62 volts if we had it at the normal 240 volts in. And we also got a short circuit current of 139.5 amps. And we can do the calculation really easy. The reactance is equal to the voltage over the current, and that turns out to be equal to 0.222 ohms. And if we want to get the inductance in henries, well, the formula for that is pretty simple. It is the reactance divided by 2 pi times the frequency, which is 60 hertz. So we can plug in the values. Over 2 pi is 3.14159, and the frequency over here is 60, and put all of that into a calculator, and what do we get? We get 0.59 millihenries, thousandths of a henry. All right, what do we do if we get the same thing for 50 amps? Well, at the 50 amp setting, we recorded a open circuit voltage of 29.3 volts and a short circuit current of significantly less, 23.8 amps. Well, now we can do those same calculations. The reactance is the open circuit voltage over the short circuit current, and that is equal to 29.3 volts over 23.8 amps, and that results in a reactance of 1.23 ohms. And we can also compute the inductance, again exactly the same formulas, and we'll just plug in the numbers. 1.23 divided by 2 pi 60, and what do we get? We get 3.26 millihenries. And that's the type of numbers we would expect. When we want a lower current here, we would expect the inductance over here to be significantly bigger. And the interesting thing, of course, is even with a certain amount of the magnetic field being shunted, the turns ratio of the transformer really governs what the voltage from one side to the other is. Now, the really neat thing is I have the operating manual for the welder. I couldn't believe it came with it. And what they did, and I haven't seen this in many newer welder manuals, but they actually have the current curves for the welder itself. And for the high current plug-in, and there are two places you can plug in the welder electrodes. For the high current one, it shows that the maximum AC voltage, the open circuit AC voltage, is somewhere between 55 and 60 volts for the open circuit test. And similarly down here at 0 AC volts out, the short circuit condition, it shows that the current range is typically somewhere between 50 and close to 300 amps. And what you can sort of imagine is if everything was dialed up, here would be the voltage current curve. If everything was dialed down, this would be the voltage current curve, and there'd be a bunch of similar curves right in the middle here. So if you're a welder, you could presumably look at this and sort of say, yeah, these curves give a reasonable amount of constant currentness, particularly at the lower levels. At the higher currents, it's not quite so constant, but it's still much more constant than if this was a conventional transformer. The interesting thing is I looked in some manuals for some modern welders, and I didn't actually see any nice graphs like that. Well, I hope you found that interesting. I should point out that good old welders like these are not the only things that use magnetically leaky transformers to limit the amount of current in the secondary winding. You find the same sort of thing in neon tube transformers and ignition transformers that are often found in oil furnaces or boilers or what have you. And indeed, I've used some of those transformers in various videos to demonstrate arcs and sparks or high voltage power transmission. The modern version of all of these things is, of course, switching power supplies. And the real advantage of that is not only do you need less copper, which is very expensive these days, but you can also control them digitally. So in theory, you can set up pretty much any voltage current curve you want that might be more appropriate for your application, perhaps different curves for different types of welding. I should thank Tesmen for sending me this clamp-on ammeter, which we used in the video. Thank you so much for supporting the channel. And if you have any questions or comments, put them below. And if you have suggestions for a future video, send me an email. Thanks for watching, and see you next time.